All right, this is a video talking about what is commonly referred to as trigonometric addition formulas. This is a way to simplify things and to use some of the laws of trigonometry to solve problems. Okay, so it's a good idea to have, most books will have a page that looks like this. Usually it's in the back of the book. And what this is a set of formulas. So these are fundamental identities, cofunction identities, and so forth. About 2 pages worth. They're in the back of most books. And right here, addition and subtraction formulas. It writes down the formulas for you. Now, books obviously are written differently. This book that I happen to use, it talked about the addition formula as being sine of x plus y. Your book might say sine of alpha plus beta, but it's exactly the same concept. Okay, so let's look at the problem. Problem says find exact value of these expressions. And I did the first one. I did A, cosine of alpha plus beta. Okay, so by itself, this doesn't make any sense. Cosine of alpha plus beta, there's a formula for it. That would be a trivial problem. What this problem is doing, though, is it's saying, hey, listen, I got certain conditions. I want you to assume the following is true. Okay, so with respect to alpha and with respect to beta, there are certain conditions. Here's the first condition. Sine of alpha is 15 over 17, and alpha is in quadrant number 1. Sine of beta is 12 over 13, and beta is in quadrant number 2. So what does that tell us? What that tells us is, here's my discussion. We need to understand 2 concepts. The 2 concepts are the addition formulas, and we need to understand how quadrants work. What does it mean when we say something is in quadrant 1 or quadrant 2? The addition formulas will tell us how do we evaluate when we add the angles inside the parentheses. The quadrants tell us how to draw the triangles, and it also gives us what the sign is, the S-I-G-N. Is it positive or is it negative? So here's something that I will refresh your memory about. I hope it's refreshing your memory. Okay, so this is from the trigonometry formula sheet. One way of thinking about the trigonometric, One way of thinking about these formulas, or these functions, I should say, is to say, okay, if you have a little triangle like this, okay, here's theta, you go out a certain length, this line segment, r, that's your hypotenuse, and then x, y, that's your coordinates. This point right here has an x-coordinate and a y-coordinate. Well, what's the x-coordinate? X-coordinate is how far out did you go in the x direction. The y-coordinate is how far up did you go in the y direction. Okay, so x direction, y direction. Well, that looks just like a triangle to me. So that's very, very similar to the other way of looking at the trigonometric functions, and that's where we just talk about opposite over hypotenuse, hypotenuse over the opposite, and so forth, the so-called SOHCAHTOA. So there's 2 ways of looking at these things, okay? So we're going to probably use both of those right now. 1 second. Okay, so the SOHCAHTOA, we need to know that. One of the conditions that the problem gave us was that the sine of alpha is 15 over 17, and alpha is in quadrant 1. So this is the easy one. This one's no problem whatsoever. SOHCAHTOA tells me that the sine is opposite over the hypotenuse. So the opposite of alpha is 15, and the hypotenuse is 17. Okay, so that's not a problem at all. Now, just to facilitate things, just to make things easier for me, I did this sine inverse, the so-called arctangent of 15 over 17, just to get an idea of what this angle was going to be. And it turns out it's about 62 degrees. You don't need to know that, but that's just something that helps me draw my cartoon. That just comes from the calculator. Now, sine of beta, that was also given to us. That's 12 over 13. But wait a second, now it's not so easy. We can't draw the triangle like we did up here because it says that beta is in quadrant 2. So beta goes all the way over like this. But one of the things that we know about how this works is that the sine of beta is going to be the same as this sine right here, but it's going to be potentially anyway is going to be a different sign, S-I-G-N. It's going to be the opposite sign. It's not going to be positive or negative, or it will be one or the other. It will be positive or negative. That sentence was not very clear. So what I'm saying is that this angle right here is going to be the same as this angle right here. The sine, S-I-N-E, the sine of this angle is the same as the sine of this angle, but it might be positive or negative, different, okay? So what do we know? Since it's in, we have these quadrants, so it's all students take calculus. So over here, the sine is positive, okay? So the sine of beta is the same as the sine of this guy, and it's the same S-I-G-N. Unfortunately, those two words sound exactly alike, so it's hard to get them straight. Okay, so since we know that, and we also know what sine inverse is, since beta is in quadrant 2, we know that it's a positive, just, sine is positive, so we can draw our little cartoon. And what do we know here? What we know is that the sine is, now we're going to use the other definition. We're not going to use the opposite over the hypotenuse. Now we're going to use this definition. We're going to use the sine is y over x. So we got, or a y over r, excuse me, y over r. So we're going to use y over r is the sine of this angle. See, the reason we have this method of doing it is because we want to have a technique for how do we define these functions, the sine, cosine, and so forth. How do we define them when we're talking about angles that are not acute? So here's one that's not acute. Well, the way we do it is we just say, okay, it's going to be the y over r. Okay, that's what I wrote down right here, y over r. So the sine of beta is y, which is 12 over r. Now, how did I know that y is 12? That comes from the given information. The given information was, where the heck is that? Man, you're killing me here. Okay, the given information was that sine of beta was 12 over 13. So I used that information. Okay, so let me bounce down here. Okay, so 12 over 13 tells me that the y coordinate is 12, and then that means that this guy right here, this r, that's the hypotenuse, is 13. That's 12 over 13. And again, just to help me draw my cartoon, I did the arctangent or the sine inverse, and I came up with what the angle is the 67 degrees. So this angle right here is 67 degrees. Okay, so now once I know these two sides of the triangle, these two sides, and I know these two sides, I can easily calculate the remaining side, right? Because of the Pythagorean theorem. Okay, so in other words, if I know that this is the hypotenuse, this is one side, this is the other side, I'm going to call this side adjacent. I can very easily do the calculation. So for example up here, the Pythagorean theorem says that 17 squared is equal to 15 squared plus adjacent squared. So then I just solve for adjacent squared, and I come up with 8. Down here, I've got the same concept. I've got 13 squared is equal to 12 squared plus adjacent squared. I solve for adjacent squared, and I come up with adjacent is 5. So now I've got my two triangles. Well, once I have my two triangles, that's the key to this. That just solves everything. So that's the hard part, is solving, is drawing these little cartoons, which is why I always tell everybody, if you're not drawing cartoons, shame on you. You're going to have a huge problem. Okay, you've got to draw these cartoons, and you've got to write down the formulas every single time. It avoids problems. Okay, so using these diagrams, and we're going to use the additive formulas, what do we get? Cosine of alpha plus beta is equal to this. Well, that's kind of messy, right? It's hard to look at. It's hard to figure it out. So what we do is we'll kind of write down the various items individually, right? We'll write them down separately just for convenience, and then we'll plug them back into the formula, okay? So for example, cosine of alpha is adjacent over hypotenuse, okay? Adjacent over hypotenuse, okay? Adjacent over hypotenuse, okay? Give me 1 second. Doggone it. Okay, so here's the adjacent, here's the hypotenuse, 8 over 17. Everybody's happy, right? 8 over 17. How about cosine of beta? Let's go here. Cosine of beta. Okay, so now we talk about cosine of beta. Here's beta. Well, it's a little bit harder to do that triangle business. So what we're going to do instead is we're going to say, well, the cosine of beta is x over r. That's one of our identities. That comes from right here. Cosine of theta is x over r. Just another way of looking at it, and it depends on the context how we do this. In any event, if we're talking about cosine of beta, cosine of beta is x over r, so that's going to be negative 5, or it's going to be 5 over r, which is 13. And because it's over here in this quadrant, because it's in the quadrant number 2, remember how that goes. All students take calculus. Because it's over here, cosine is going to be negative. So that's what we get right here. Cosine of beta is negative 5 over 13. Okay, so as I said, it all comes from these cartoons. How things, once you draw the cartoons, you got everything you need to know. So sine of alpha, and sine of beta. I'm going to sine of alpha, let's take sine of beta. Sine of beta is y over r, so that's 12 over 13. There it is. Boom. Okay, so what do we get? If you take all of these guys right here, one at a time, and plug them into this formula, here's what you get. Okay, I'll let you do that yourself. You plug those in, multiply them out, and you get this. And that is the correct solution according to the solution set that I was given. Thank you.